Okay, so good evening, everyone, and welcome to today's Vancouver Kimberlite Cluster Seminar, and thanks to everyone for joining us today. My name is Amy Maley, and I am a master's student at UBC, and I'm this year's VKC host. I also have with me here virtually Maya Kopolova, who is our convener. VKC is a series of seminars for diamond geology and related topics, and our goal is to bring academics and industry professionals together. I would like to acknowledge SRK Consulting for being a longstanding VKC sponsor. And I would also just like to share a few quick Zoom housekeeping notes. Just please make sure that your cameras and your microphones are turned off throughout the duration of the presentation. And the presentation will be about 50 minutes long. So please keep your questions until the end, at which point I will help to facilitate a question and answer period. And then after that Q&A period, we will stop recording and move on to a little bit more of a casual social hours where we can chat more informally. So now I would like to introduce today's speaker. So I'm happy to introduce Dr. Seogi Kang. Dr. Kang completed his PhD in geophysics at the University of British Columbia in 2018. His thesis work focused on computational electromagnetics and its application to mining problems. Currently, he is a postdoctoral researcher in the geophysics department at Stanford University. His research interest is in maximizing the value of geophysical data to contribute to the solutions of challenging geoscience problems. He is a co-creator of an open source geophysics package, SimPeg, and a core contributor of open educational resources, GeoSci XYZ. So with that, I would like to pass things on to Seogi here. So if you could just share your screen.
Okay, can everybody hear me? It's always nervous, like there's a fear that nobody hears my voice. Anyway, thanks both Amy and Maya for giving me an opportunity to have a chance to talk about geophysics in the Vancouver Kimberlite cluster in seminar series. And as actually Maya said before, she said this is it takes 8 years to give a geophysics talk in VKC. So I'm a little bit nervous. So I have a bit of responsibility to do a good job. So I'll do my best. So what I'm going to talk about is first successful delineation of Kimberlite units using multiple airborne geophysical methods. And those are my core collaborators. So the talk, like the presentation that I'm going to show you today, it's a 3-part papers that we wrote in 2017 in a journal called Interpretation. And we have used 4 different airborne geophysical methods to obtain 5 different physical properties. And then by using that, we created a 3D geological model that can delineate the different Kimberlite units. So what I'm going to show you today is sort of the gist of these 3 papers. And these 3 people, Sarah de Vries and Dominique Fournier, Douglas Oldenburg, were like sort of the 3 major authors of this paper. And there are many other people who contributed this to this research, which I'm going to thank at the end of this talk. So kind of want to start with how diamond forms. I'm not an expertise in diamond geology, but I'll try to do my best. So how diamond forms, it starts from a lower mantle, and then it starts from here, and then deep volcanic eruption transport the diamonds to the lower crust like this. Okay, and then at the lower crust, there can be a multiple eruptions forms a Kimberlite pipe like this. So the multiple eruptions important because diamond distribution in the Kimberlite pipe depends upon this above emplacement process. So you actually don't, like each eruptions makes some sort of deposition of diamonds into a pipe, and there are multiple eruptions. So you actually don't know which Kimberlite unit is diamondiferous. That's sort of the major challenge that we're up against. In the context of diamond exploration, as well as the economic evaluation of diamonds. So if I zoom in here, like this is a kind of typical conceptual diagram of Kimberlite pipes, there are many different units like pyroclastic, diatremes, and epiclastic, crater faces. But the bottom line here, we actually don't know which Kimberlite unit is diamondiferous. So that gives us a motivation to obtain a sort of reliable 3D geological model. And if you can obtain this reliable 3D geological model, that can be very, very useful from all the exploration to economic evaluation. And sort of the size of the kind of problem that we're dealing with is about kilometer by kilometer area and 500-meter depth. And that's sort of the size of the pipe region. And obtaining this 3D model is all the better. So if you can obtain reliable 3D geological model at the exploration stage, it could be much better. And then if you can obtain that at the very late economic evaluation stage, you may lose a lot of information and you may make a lot of there's higher chance to make sort of wrong sort of decision, especially like if you think about the drilling location or locating the bulk sampling location and stuff like that. So the question then, how do we obtain a 3D geologic model? And what is a typical way that has been done for various Kimberlite pipes? So the first one is drilling. It's obvious methodology. You can drill many drill holes and then sort of build up the 3D geological model. Because if you have a drill hole, you can get a core sample. And the process of the drillings, it provides an accurate point information about the geology. And also it gives you direct information about the kimberlites. So that's great. But the downside is it has a very, very small sampling volume, less than a meter. Okay. And then that means between the wells, it looks like lots of well data. Between the wells, it could be a pretty large data gaps, right? And the cost is relatively expensive. Okay. And the second one is bulk sampling. So you can think that as like a much greater scale drilling. So it sucks up lots of rocks, in thousands of tons from the subsurface. So what it provides, it provides much larger sampling volumes compared to the drillings. And it can also provide much more detailed information about diamonds, like a size distribution, grades. And this is very critical for economic evaluation. And the downside of the bulk sampling, still, I think it's larger sampling volume than the drillings, but about thousands of tons. But compared to the entire pipe, it's still a small sampling volume. And there could be large data gap. You usually have one bulk sampling or two. So there could be large data gaps and the cost is still very expensive. Okay, so those are sort of the typical methodology that we're using. And so to fill in this data gap, airborne geophysical techniques can be actually useful. So airborne geophysics, you use some sort of aircraft like a plane or a helicopter, you inject the energy into the subsurface, measure the secondary signals coming from the subsurface, and you measure the data. So what it can do, it can rapidly map out the large area and a typical speed about 100 kilometers per hour. So you can map a really, really large area very fast. And what's important is it is sensitive to the large scale features. So it has much greater sampling volume compared to the drilling method. And the cost is cheaper, much cheaper than either drilling or the bulk sampling. The downside though, what it provides is an indirect information. So what it provides is, for instance, if you do a magnetic survey, what it provides is a distribution of magnetic susceptibility. If you do a gravity survey, what it provides is a density distribution. And again, another limitation, the resolution of the methodology is limited. Okay, so those are sort of the downside of this method. And so what it provides, what it provides is the physical property or geophysical property. And what the challenge that we're up against using geophysics is non-uniqueness of a geophysical property. Here's an example of magnetic susceptibility from low to high. And there are many different rock types. So for instance, kimberlites between 10 to the minus 2, 3 to about 0.2-ish. And if you think about the granite, that's really large range. And if you put a point here, if you got the single physical property value of susceptibility, it could be kimberlites as well as the granites. So these are sort of the challenges that we're up against. So for a given physical property value that we can obtain from the geophysics, it is pretty hard to determine the rock types. So those are the challenges that we're up against. And I'm going to introduce several airborne geophysical methods now. So the potential field method, like gravity and magnetics. So gravity, if you have a lower density, you can measure the low anomaly. Magnetic method, if you have a high susceptibility value, you can actually measure high susceptible anomaly. And what you ended up getting is like a map like this, a single map, okay? But you can cover a large area fast. And if you think about, you're getting only one map, so it could have a good lateral resolution. So you can, if you have a pipe, you can kind of figure out what is the lateral extent of the pipe, but the depth-wise, it has pretty poor resolution. So that's the downside. And there's another method, electromagnetic method, called EM. And what EM provides is, rather than a single map, it provides a multiple maps. And it's a function of time. As you go like a later time, you see a deeper part of the subsurface. So it actually have much greater depth resolution compared to the other potential field method. And if you put a point here and look at the data, that's what you're measuring, a decay curve. If you have a conductor, for instance, Kimberlite can be a conductor compared to the host granitic rock, and it'll decay slowly. If you have a resistor, like a weak conductor, like a granite, and it'll decay very, very fast. Okay? So those are sort of the methodologies, airborne geophysical methodology that we're going to use today. And it can be sensitive to electrical conductivity as well as the chargeability. I'm going to explain the chargeability a little bit later. So by using the multiple airborne geophysical method, we can obtain density from the gravity and magnetic susceptibility from the magnetics. From electromagnetics, we can obtain electrical resistivity and chargeability. So let's think about what is the typical sort of physical property values of the kimberlites. So overall kimberlites, it's likely have a lower density than the granitic host rock. So granitic rock likely have a higher density. And the pyroclastics and volcaniclastic units have higher conductivity and higher chargeability. So pyroclastic and volcaniclastic is an extrusive, so it's exploded and then exposed to the surface. So it's much more volatile. Where diatreme and hypabyssal phases, it's an intrusive unit. It's likely have a higher susceptibility and it's a more intact rock. So those are sort of our expectation. And so by kind of having density model and the magnetic susceptibility model and the electrical resistivity and chargeability model. So by having multiple physical property distribution, which senses different parts of the different kimberlite units, we have some chance to kind of differentiate these geologic types or kimberlite units. Okay, so this is the sort of the value of having multiple physical property distributions. Okay, so that's sort of what we're going to do today. And the sort of overarching question that I have is how much kimberlite information can be obtained from only using multiple airborne geophysical method? That's the question. And what we're going to do is building a pseudo-geological model for a kimberlite deposit. So from airborne geophysical data, we want to build some sort of pseudo-geological model in 3D. And today I'm going to show one case study, Do27 Pipe in Northwestern Territory, Canada. So this is an aerial image of the Do27 Pipe. As you can see, there's a lake. And below this lake, Do27 Pipe is located. So obviously, it's a bit more challenging target compared to the other location, the other pipes which is exposed to the surface. So Canada is world's third largest diamond producer. I'm not sure that is true at this point, but at some point that was true. And the Do27 Pipe is located near Lac de Gras in the central Slave Craton in Northwestern Territory. So that's the Northwestern Territory, there's our Canada, and that's the Slave Craton. And this is the location where diamond pipe can be present. And there are quite a few, actually, other kimberlite pipes discovered. I think at total, there's about 300 kimberlite pipes in the Northwestern Territory, as far as I understand. And the two big ones, Ekati and Diabic, they are in production, I think. And Do27 and 18 pipe is located here, okay, pretty close to Ekati and Diavic. And if I zoom into that area, that's how it looks like. So that's the lake that I have shown in the beginning. And that's the Do27 pipe located at the southern part and Do18 pipe located at the northern part. And like previously, this Do27 and 18 pipes are referred to as a T Kwai Cho Kimberlite complex. This complex was discovered by Airborne geophysics in 1992. But today I'm going to focus on Do27. Okay. So in 1992, Do27 pipe was discovered by using electromagnetic and magnetics. And both data were taken by Airborne geophysics. And this red color means the high conductivity anomaly. It means EM, if you have a high value, there's more conductive materials. As I said, Kimberlite could be more conductive compared to the granitic host rock. So both this Do27 and 18 has some chance to have Kimberlite. And if you look at the magnetics, this Do27 pipe also shows the magnetic high. So by having both, like people were relatively confident, there could be Kimberlite pipes. Do27 likely has a greater chance to have more Kimberlites. That was sort of the decision that they have made. In 1993 to 1994, based upon the magnetic data, looking at like this, and this is sort of the control line of a high magnetic anomaly, they drilled the 44 wells at Do27 pipe around in this location, so northeastern side of the pipe. And after that, they rushed to a bulk sampling, and then they bulk sample about 4,000 tons, which is a large amount of rocks. And that bulk sampling is finished in 1994. And the result of the bulk sampling was following. So this is sort of like based upon drillings and bulk sampling, that's the conceptual model. They said, oh, here's a lake. And below the lake, there's a thick till, it's about 50 meters. And below the till, there's a thin PK unit, like around that AA prime. And below that, there are diatreme faces, fractured and much more complicated. And their evaluation about diatreme phase is about only 1.3 carat per 100 tons. Okay? And for PK, just a thin, small unit, was 36 carat per 100 tons. Sorry, I missed the H. It's 100 ton for pyroclastic Kimberlite. And this 1.3 carat per 100 ton for diatreme phase actually, because of this, it did not produce the anticipated high grades. And then it led to a catastrophic Canadian junior market crash and abandonment of the project. So kind of determination of this diatreme phase and the volume based upon whatever the geological model they had at that point actually led this decision and abandoned the project, which was a huge impact at this time. And kind of thinking about this early 1990s, this was like sort of the prime time where lots of money was invested for diamond exploration in Canada, and many Kimberlite pipes were, I think, found. And I think both Ekati and Diavic was found about this time, I guess. Okay, after that, in 1995, some geologists reevaluated the drill course and interpret the PK as a volumetrically dominant unit. So it was quite different from what's shown in the figure. So PK, if you go to the lower southern part, PK was actually a volumetric dominant unit. So that people could have made that interpretation, but they didn't. And between 1995 and 2005, nothing really happened. And in 2005, I think it was a Peregrine, a new company, revisited and then proceeded the couple of bulk sampling and extensive core drilling. And by doing so, this was the result of bulk sampling. So the PK, and that was sort of the latest model that they got. And if you look at the PK, that's a PK pyroclastic Kimberlite unit, has a large amount of grade, like 90 carat per 100 tons. So this was sort of like the new model that they've got, but that was sort of the 994 model, which sort of they made them kind of abandoning the project. So this was sort of kind of the wrong targeting exercise that really kind of lose the chance that they could have developed this deposit. Anyway, so that's what's been kind of what's happened in the Do27 pipe. And with that bit of excitement in the beginning of the discovery of this deposit, there were actually lots of airborne geophysical survey has been done. In 1992, there were EM and magnetic survey. In 2001, there was a gravity survey. 2003 and 2004, there were a couple of other types of electromagnetic survey has been done. So this kind of shows excitement in the geophysics side. Oh, we could use the geophysics to find a diamond deposit. And so here's example data. So this is a gravity data. And it's about 1 kilometer, about 1.5 kilometer. And that's, so white line shows the outline of the lake. Okay. And that's the Do27 pipe and Do18 pipe. And based upon this gravity data in 1993, people had somewhat wrong conceptual model. Oh, these pipes are connected. Okay. So this is another kind of a bad example how just looking at the data, interpreting the anomaly could kind of lead into a wrong conceptual model. Yeah, like what the gravity sees was the overall kimberlites, because the kimberlite has lower density compared to the granitic host rock. And this is a magnetic data, which actually has used to locate the drilling target in 93 and 1994. And that was at the northeastern side of the pipe. And that was actually the major reason why they drilled there. And that led to kind of this catastrophic event. And the EM data and the Ollie time. So as I said, EM data have a multiple time channels. And then Ollie time data can see the electrical conductivity. So high value means the high conductivity anomaly. And there's a theoretical proof EM response is always positive unless like there's a certain condition. And that condition is the chargeability. If the subsurface material has a chargeable materials, that could have some sort of negative values. And that's what we have observed. There are some negative anomalies over Do2017 and Do18 that meant there are some negative values, like there's some chargeable materials. I'm gonna explain what's the chargeability right after this. And if you go to the layer time gates, you see much stronger negative anomaly over Do27, okay? So that means like at this location, there are some chargeable materials. So let's actually think about what is a chargeability. So chargeability, you can think that rock as in a microscopic scale, it could act as a capacitor. So suppose you have a pore like this, like a pore fluid like this, and then it's filled with some fluid. There are some ions. So if you put an electrical field as a forcing function, then the charge will start to build up, okay? So what's happening, so we're putting the currents to make a forcing function. And then like if you measure how the voltage look like in this system, the voltage will start to increase slowly, okay? And then after the shut off and decays. And that's because of this polarization process. If you don't have any polarization process, the output voltage will same as the input current. And the beauty of this method is like, depending upon the materials, this decay rate is actually different, okay? And then this decay rate is related to the pore size. And some clay materials are chargeable. And the volcaniclastic and pyroclastic, it's exposed to the surface. So there's some chance to include some clays or other sediments, okay? Likely, the pore size of the volcaniclastics is less than pyroclastic. So pyroclastic is much more volatile and volatile sort of explosion. So it'll likely have a greater pore size. So what we expect for pyroclastic, it's a slow decay, and the volcaniclastic likely faster decay. Okay, so that's sort of the expectation. Okay, and so this is sort of the summary of the data that we have observed at Do27 pipe. So those are sort of the geophysical anomalies. This for gravity anomaly, magnetic anomaly, so gravity low, magnetic high, conductivity high, and the negative anomaly showing the presence of chargeable materials. So this like a collection of airborne geophysical data is a great data for discovery of a kimberlite deposit, which can be used for diamond exploration. But what we want is a 3D geologic model today. So we're going to move forward. So we have the data, but what we want is the three-dimensional image of the subsurface. That's what we want to see. So what we need to do, we need to apply a process called inversion. So what the inversion means, we want to find a three-dimensional resistivity model like this, a density model in this case, that can fit the measured data. So you can obtain the 3D model from the geophysical data. And well, this is great, but the problem is that this inversion process is non-unique. That means there can be many different models that can fit the data. So there could be a large amount of uncertainty. So there could be two solutions. The solution one, you acquire more data. Solution two is you can add relevant prior information that you can obtain from geologic knowledge or drill course. We're going to focus on solution one. Okay, and because given our goal is, okay, what can we do just using the geophysics to obtain information about the kimberlite? So like if you have, rather than having a single data, if you have 4 different data set, you can have 3 different physical property model. By having multiple 3D models, 3D geophysical model, you can sort of narrow down the uncertainty and kind of generate the pseudo-geologic model that can delineate the different kimberlite units. So that's what we want to do. Okay, so I'm going to move on to the density inversion. So what I'm going to do now, I'm going to invert each data set separately. So I'm going to start with the gravity data, which is the density inversion. So this is our gravity data. And if I invert that, so if I find a 3-dimensional model that can fit the data, it looks like that. And what I'm showing is the plan view map at the 100-meter depth, and it's about a kilometer scale is east to west and south to north. And again, this east to west and the depth scale. Okay. So you can see this blue is like a density low. It's a negative density anomaly. Okay, so it's a lower density compared to the granitic coast rock. And you can see sort of the pipe shape. So what we see is sort of the overall kimberlites. And if you do the susceptibility inversion, so this was the susceptibility, like magnetic data. And if you invert that, that's the susceptibility model that we're getting. So we are seeing the high susceptibility anomaly at the northeastern side of the pipe. And if you look at the depth section, you can see this kind of features. Okay. And the third one is conductivity inversion. We're using the EM data at early time, where we don't have any chargeability effects. And that's what you can get. So this is the recovered conductivity model. Red color means high conductivity. Blue color means low conductivity. So low conductivity in this case likely correspond to the granitic coast rock, and the high conductivity corresponds to kimberlites. So you can see it actually puts the conductor at depth, right? And the fourth one is a chargeability inversion at intermediate time. So if I took an EM data at intermediate time, it contains both conductivity and the chargeability information. I'm not going to go through the details, but what we need to do, we need to decouple EM and this conductivity and this chargeability signal. If you're really interested in, I'm happy to answer later, but here we decoupled and inverted the data. So that's the resulting chargeability model that you can get. So you're getting quite different distribution, right? So white color means the high chargeability. And if you go at the very late time, and where chargeability signal is dominated, then if you invert that, and that's the chargeability model that you get. So this 2 chargeability model provides a different information about the kimberlite. Okay. So we got 3 different data, but we were able to get 5 different physical property distribution. Got the density model, susceptibility model, conductivity model, chargeability model at intermediate time, and chargeability model at late time. Okay. So with this 5 different physical property model, what we want to do, we want to build a 3-dimensional geological model that can delineate kimberlites. And even just looking at that, these models are different. That means we have actually a chance to delineate different rock types and likely kimberlite types. So that's the next step. we're going to construct a pseudo-geologic model. So starting from the density model, we're going to find a certain threshold. So the rock unit 1, which is an olive in color, is a low density. So from the density model, we can sort of like carve out all this like high density values and then leave the low density value. And that's how it looks like. Okay. So you see kind of the outline of the pipe at the plan view. And that's sort of the pipe shape that we were able to get from the density. So as I said, lower density than granite host rocks. So likely this low density anomaly is the overall kimberlites. And if you add the susceptibility, R2 yellow unit, it's a low density and high susceptibility. So that shows up at the northeastern side of the pipe. And actually that was the location that they drilled because they thought at that point, this is the diamondiferous unit. And it was sort of led to a failure of the exploration. And likely it could be a diatreme or a hypabyssal intrusive and intact unit. So if you add the conductivity model, R3, the blue color, it's a low density, moderate susceptibility, and high conductivity. Okay, and that's the blue unit. So this is actually more, it's closer to the later model where they reinterpret that as a PK unit. And if you add the chargeability model, two different, and R4 is from the intermediate, high intermediate chargeability. And so red color. So as I said, intermediate has is connected to smaller pore size. So you can interpret that later as a VK unit, but R5 is still higher chargeability, but it was shown up at the late time gates. So it could be connected to greater pore size. So red color, smaller pore size. Green color, a greater pore size. That's what the chargeability information provides. And yeah, look at that, you see kind of different delineation of the rock types within the Kimberlite pipe just using the geophysics. And that's what you can get from multiple airborne geophysical data. So that was kind of what we were able to obtain. And that's the 3D view of the pseudo-geologic model. Again, so what we interpreted R1 as overall kimberlites, R2, it could be a diatreme or hypabyssal kimberlite. R3, mostly from the conductivity, is either PK or VK. And R4 was a smaller pore size, likely VK. And R5, a greater pore size, likely PK. Okay, so that's sort of our interpretation. And HK means hypabyssal kimberlite, VK, volcaniclastic kimberlite, PK means pyroclastic kimberlites. Okay. So that's what we were able to do. And let's actually, they were in between 2005, in 8, I guess, in that duration, there were many drillings. And then they actually built much more fine-grained geologic model. So let's actually compare what we built as a geophysical model to a 3D geologic model generated by many drillings. And this is the same plan view map at 100 meter below. This is a geologic model that they built with many drill holes. So the black dots shows the location of the drill holes at the surface. And this black dashed line is the outline of the PK pipe, which they interpreted as a diamondiferous unit at the surface. So you can see some sort of correspondence between these units and this outline. And the green color means the PK, and the red color means VK, and yellow color means HK. And that's what we were able to get from the geophysical model. So they're actually quite similar, and then almost surprisingly similar. Okay, so I think we're doing a great job in the lateral sort of resolution side. And if you look at the vertical section view, that's how it looks like. So I will also laid out the outline of the pipe from Harder et al. I think I missed I think it was 2006. Sorry about that. So that's the black line. Okay. And in this geologic model, this sort of till color, it's a glacial till. So as I said, the pipe was below the lake, and then below the lake, there was a till about 50-meter thick. And that's the till. And below the till, there's this like a large PK pipe and VK and HK unit. And that's our geophysical model. Well, not as good as the lateral, because as I said, our geophysical model have a limited resolution. Although we added multiple geophysical model, it has still some limitation, but still, like given what we did is just using the geophysics, we did actually a pretty good job delineating geophysical model. And that's the three-dimensional view of 3D geologic model from many drillings, and then geophysical model from 3 different geophysical data. Okay, so that's kind of what we've done, but let's kind of think about, let's looking backward. And what if we had this geophysical model in 1993, which they made sort of critical decision. And what, like kind of recalling what they've done, so based upon this magnetic anomaly, and they have, and then with some sort of drill holes, they had this model. Okay, and then major sort of this like a kind of trigger was this diatreme phase with having very small grade, like 1.3 carat per 100 ton. And that actually triggered the decision, oh, okay, we're not gonna move forward with this diamond deposit. Okay. And that was sort of the drill target in 1993 based upon this, the magnetic data. And if we had this model, and then that actually led to long drilling target in 1993. And if we had this model, it was pretty clear, like this part, this is this like southern part is the main pipe. And they would have drilled more. And then if you had like a few drill holes that can sort of confirm that conceptual model, they wouldn't kind of drilled here, or they wouldn't actually go to, they wouldn't do a bulk sampling around there. And that wouldn't kind of led to a decision of abandoning the project, I guess, because this is the diamondiferous pipe, and the carat per 100, like the grade of the PK was actually pretty good. It was about 90, or average 90 carat per 100 ton. Okay. So I think that kind of shows sort of importance of having a reliable 3D geologic model in the early stage, as early as possible, to guide the important decision, likely, like for instance, like locating where do we need to do a bulk sampling. Okay, so I think, so we kind of went back and thought about like the value of having reliable 3D geologic model and how airborne geophysics can actually contribute to that. And what I want to talk about is a little bit more is what's the future? How can we really maximize the value of airborne geophysical method for diamond exploration and economic valuation? So this is a table from another VKC seminar. I think it was Brandon. And what it shows is this is a time, and then it's amount of money invested for diamond exploration. And obviously, I think this was actually a good period. And as I said, I think early 90 was sort of the prime. And then with that prime time, there were much more investment happened. But around this time, it's kind of plateaued. And the major reason why is a great discovery of Kimberlite deposit is stalled. That kind of led to this decreasing investment in this time. So if we want to trigger more investment, we need to discover we need to find a great Kimberlite deposit. And the challenge that we're up against, these ones have found. And so it is time to discover challenging ones. And what I meant challenging one, it could be below the overburden, not exposed to the surface, and has more complex geometry compared to the typical pipe-like structure. And Do27 that I have shown was actually a challenging target. It was covered by a lake and the thick overburden, about 50-meter thick. And it actually had a complicated geometry different from sort of the typical Southern African type pipes, like an Akkadian diameter. So this diameter phase and this kind of really pipe-like structure the PK was, this Do27 was quite different. It's more like a SIL complex, which was more complicated. Okay. So kind of what we have learned from Do27 can be transferred to find more challenging targets. And acquisition of multiple geophysical data can lead to a discovery. And as I've shown, gravity, magnetic, EM, and chargeability could actually give you narrow down this discovery process and can be very helpful. And I'm particularly excited about the chargeability anomalies, which is a negative EM data. This was actually basically my PhD. And this is a new technique. And the reason why we can do this now is because of the improvement instrumentation, because this chargeability signal is very small. So with the improved signal to noise ratio that we have now, we can actually consistently measure this negative anomalies, which is very small signals. And Do27 is not the only case. So in another example where they found this negative anomalies and used that to kind of find Kimberlite deposit is in Russia. It's not sure, I cannot really read, but this deposit, I'm not sure that's discovered, but there was a study that they have shown, this Airborne data showed negative anomalies over this Kimberlite deposit, and they interpreted the data and recovered the conductivity model like this and chargeability model. So yeah, it's not the only case, and then I'm pretty sure we can see more case history that this airborne EM data and negative anomalies is used to find Kimberlite deposit. And I want to emphasize the EM and obtaining a three-dimensional conductivity. So if you think about the challenging part is seeing below this thick till, about 50 meters thick. And neither gravity and the magnetic data, it suffers from the depth resolution, but the EM actually have a greater depth resolution. So what we were able to do, we were able to actually nicely image the conductor below the till. And that actually has some value. And also kind of just thinking about the volume of the PK. So if I just use the EM and then cut the find the threshold value and generate the volume like this, I can get pretty good estimate of PK in terms of the volume. So I think this can also be used to estimate the volume. And as I have kind of shown in the vertical section, we've done our best just using geophysics to generate the 3D geologic model. In the plan view map, it was actually pretty good, but the vertical section, it wasn't that good. And in 3D view, it kind of shows, yeah, it's not as good as the geologic model as expected. And especially this HK unit, which is a thin kind of plate-like structure, we kind of overestimated. This is yellow color, right? So yeah, what we've done is absolutely limited. And what can we do to obtain a more accurate model? And what we can do, we can actually integrate geophysical and geologic data. So that's what we're moving towards. And this is a situation where you got the geophysical data, and then you may have some drill holes. And this is actually the drill cores that we've got from Peregrine. And this is the PK unit. You can see there are some clays. So my guesstimate wasn't too bad. So there were some clays. And so if it was making sense, it was actually true. And this is the VK unit. So you can see some olivine. And this was the HK unit, more intact, a hard rock unit. So if you have some drill cores like this, you can actually integrate that information. And that was the solution too, right? Our inversion process was suffering from this non-uniqueness. So by adding relevant prior information from drill cores or geologic knowledge, we can actually improve the accuracy of the three-dimensional image. And this is the work from my colleague, Thibaut Estig, currently working at Cobalt. And what he did, so he used the same data, gravity data and the magnetic data. And he supposed that, if we have one drill hole, and if we integrate that and assume that we know there are three different geological units, how much improvement that we can make. And he was able to make much greater resolution by doing so. So this is sort of like a kind of a way to go rather than separately inverting the data and then generating a pseudo-geologic model. You can invert all of the data and then put a constraint and also add the information from the drill cores. By doing so, you can get much more accurate three-dimensional geologic model. So that's sort of the future and we're moving toward. And this could be very useful once a few holes and are drilled and look for allocation for bulk sampling, I think. So that was it. Here's my conclusion. And as I mentioned many times, airborne geophysics can be very useful from diamond exploration to economic evaluation. And especially multiple geophysical anomalies can be useful for a diamond exploration, for a discovery. So we have shown gravity, magnetic, EM, and a negative anomaly from EM data that can show the chargeable materials. And accurate 3D geologic model is the key for both exploration and exploration. And what we have shown was sort of the first successful construction of the 3D geophysical model, delineating the Do27 Kimberlite pipe. And we only used the geophysical data. So from this 5 different physical property model, we generate the geophysical model that are relatively similar to the geologic model generated from many drill holes. And this technique can be very helpful at early stage when there are not many available drill holes. And by intuiting geophysical and geologic data, that can provide much more accurate estimate of the 3D geologic model. And I think that could be the future. And to finalize, I hope to see great discoveries guided by airborne geophysical data and more use of inversion techniques to build 3D geophysical model for diamond exploration and evaluation. Thank you very much.
Thank you very much, Seogi. That was very, very interesting. We're going to start the question and answer period right now. So if anyone has any questions, feel free to either ask them in the chat or just speak up. There's not like a crazy amount of people in here right now. So if you want to speak up, that would be totally fine too. I just had a quick question to just kind of start things off. I'm not a geophysicist by any means, but I did have a question when you were talking about the chargeability, and you were talking about how you have sort of your intermediate and your late time. Is that the time in which the signal takes to come back to the sensor, or is that related to depth? I wasn't quite understanding like the early, intermediate, and late.
Great question, because I sort of mushed out that part because there are quite a bit of details going on, and 1 hour is not enough to go through all the detail. But what's happening? So if you measure the time, like a time domain EM data, so what we are measuring is the time gates. So early time. So forget about the chargeability. Early time is the near surface, and late time is the deeper part. Okay, so that's the typical understanding. But if you have a chargeable materials, then what's happening, it could actually polarize the currents, and that generates the direction of the currents. And what you measure is the negative decay. Then that usually comes in at the later time gates. So it's not necessarily about the depth information. If you see the negative, and it's likely at the late time gates, and that is the sort of the proof of the presence of the chargeable materials. So that's in the intermediate time. So that's the time zone where you have a conductivity signal as well as a chargeability signal. So both of them are existing. So that was the reason why, if you look at that map, there were some positive values and negative values.
Okay, thanks. Do any of our geophysicists have any questions for Seogi?
I want to get some questions from the geologist.
Hi, Seogi. It's my name's Mike. Great talk. Another I don't know, maybe simple question for you from a non-geophysicist like like Amy. You'd mentioned briefly, you made a comment during your presentation about the need to decouple EM and the chargeability. I believe it was EM and chargeability, or it might have been another feature, but you said that you might get back to explaining after the presentation why it's important to do that.
Yeah, let me reshare. Okay, so this is a typical example. So if you look at that, the blue color means a negative, right? And the red color means positive. So there's some signals due to the conductivity, there's some signals from the chargeability. So somehow you need to decouple it to invert for either conductivity or chargeability. So that's the need, because it's a different signal. And then it actually has a bit of different physics. So if you don't take into account that, you're going to get wrong answer. So the first process is decoupling that conductivity signals and chargeability signals first, then invert. That's sort of the process applied. Is that kind of clear?
For the most part, yeah. Again, the time's obviously limited, and we don't have much of it to obviously go into all the background and the underlying math. But for the most part, I think that covers it. Thank you.
Yeah, but if you go to late time, this is the time where the chargeability signal dominates. So in time, there's a natural separation, but there's a certain intermediate time where both conductivity and chargeability signal is considerable. And that's the reason why we need to decouple it.
Hi there. I've got a real quick one for you. Sorry, Mike, hopefully I'm not interrupting you. If you wanted to respond there.
No, go ahead, Daryl. Thanks, Seogi.
Just wanted to say, wow, that model is awesome to look at, and from what I gather, completely unconstrained inversion, and it did a heck of a job. So that's really cool to see. And just real quick, frequency domain EM data. There was none of that integrated into the process here, I don't think, was there?
That part also I kind of because I didn't want to mention frequency domain and time domain. So this is actually the frequency domain data. Sorry about that. Because I thought that could overcomplicate the process. So this one was frequency domain data. And those two are time domain data. Yeah.
Yeah, right. And no modeling was done with the frequency domain, I think. Was
it? When we invert the conductivity, we jointly inverted the frequency domain and the early time gates of the time domain data.
Okay, perfect. Thanks.
Yeah, that was a bit of technical details, and happy to answer. But
may I ask a question?
Sure.
I'm translating a question I received in Russian from my colleague Yuri, who is a geophysicist, and he participated in discoveries of Siberian kimberlites, and he is asking you, Seogi, to what extent when you did your inversion, to what extent you used the data in drill holes and other local geophysical drill hole information, like exploratory, has the exploratory geophysics been done there? And did you have those data on those drill holes available to you? Or you use only geology and no drill hole geophysics?
So for that 3D inversion, we didn't use any other information. We only used the geophysics and the minimal prior information. So what I meant prior information is the subsurface property changes very slowly in space, smoothly in space. That's the only prior information that we have used. So that was sort of our kind of frame. Okay, we're not going to use any other data. We're just going to use the geophysics data, how far we can go. So that was it, yeah.
Mm-hmm. Thank you.
Except for Thibault's paper, right, Sog? Thibault,
yes. Thibault's paper was different. He used many other prior information, and that's what I meant in the future. Well, he's already done it, so it's not maybe not the future, but using in the real setup, I think it's still the future, I guess.
I have another question. So you had mentioned potentially using this to find new discoveries under a lot of overburden, but you were also talking about too how your resolution at depth isn't great. How deep are you talking about in terms of when you start to lose that resolution?
For EM, I think we were able to see about 400 meter, I think. And then, yeah, so I think, so what I meant depth, like a limited depth resolution is mostly for potential field data. So going back, so potential field data only provides a single map. And when you can invert that and obtain a three-dimensional model, but it still suffers from the depth resolution. But the EM could have much better depth resolution. So that's sort of why I kind of emphasize the value of EM in the context of imaging the three-dimensional pipe. So that image that I have shown at the very end. So this is actually the conductivity model that we've got. And then I think the bottom was about 400 meter. And in a Canadian setup, I think we can see up to 400 to 500 meter with the existing EM system.
Awesome, thanks.
I have another question from Yuri, if I may go ahead with that. So Yuri is asking, how do you explain the mismatch between the geological and geophysical models?
Mismatch between geological and geophysical model?
Geophysical, yeah.
That was absolutely expected because, as I said, where is that? Well, inversion is a non-unique process. So there are many different models that can fit the data. So we did our best using some prior information to obtain a model. But yeah, what we're getting is not necessarily the true model. So that's sort of why I kind of suggested, like, we need to integrate more information to get more accurate geological model from the geophysical data. And obviously we need some sort of drill hole information. And by doing so, we can get closer to this geologic model, I guess. And then this was an example. So that was the slide. And this was an example research that has been done. Yeah, so I hope kind of to transmit that this like a geophysical inversion is useful, but there is a large uncertainty. So the image that you see from the geophysical data is not necessarily true. And so the sort of the first order sense of the image, you can get it, but you may not over interpret that as a true model. That's sort of like kind of one of the messages that I want to transmit.
Hi, Sagi. Thanks for your talk. So I have a quick question.
Hi, Sharon.
Hi. So how did you determine the cutoff values for the each physical property models?
That's a very great question, and I think I don't have a great answer. I think we did many iterations, and yes, the only thing that I can explain, like for a given geologic knowledge of, okay, there's an HK, PK, VK, and then a rough, like an estimate of medium, high, low resistivity, conductivity, and susceptibility, we kind of subjectively have chosen. So one could have generated different 3D geologic model, but I guess the first order feature wouldn't change, even if one picked a different sort of value, I guess.
Yeah, I see. Another quick question is, I noticed that the pseudo-geological models consist of the 5 different units, and is each unit derived from one physical property model? Let's say the R1 from the density.
No. I think it was from all 5 different physical property models.
I see.
So, but I showed the step by step which one is mostly from.
Oh, okay.
Which one?
I see.
Just to simplify the process.
Cool.
If I recall correctly, Sug, I think the cutoffs were determined based on the volumes, right? We're basically like charting like how much volume we were bringing in and kind of picking some sort of corner, you know?
Yeah,
too much volume.
I don't exactly remember them, so and I think it was still subjective. So I think I don't have a great quantitative answer how to pick the vessel's value.
So can we go to the slide that you showed, one of the last one, when you introduced that New York by Astic by Tibor, and you showed, yeah, this one, that picture on the left. So what are those ISO lines that outline those two round features there? And
right. So
what's there and why HK, like all that black points there next to HK, but not in the center of that round feature?
So yes, I didn't really explain. So what Thibault did, so when you're jointly inverting multiple geophysical data, you need some constraint linking different physical properties. And Thibault's idea was, okay, suppose there are like several geologic units. In this case, PK, VK, HK, and the background. Okay, and then you're gonna kind of like generate some sort of mapping function, a function that, okay, like this is the susceptibility and density space. So there could be some sort of probability function that, okay, so this high probability, then it's likely PK, and this high probability likely HK, this high probability likely background. So you can actually start with some sort of the probability function, and then within the inversion process, you can actually update that, right? So this point, I think it's the resulting distribution that he were able to obtain. So that's the model in this 2D plot. And so that's, I think what's shown below is the prior that you started, but as you update it, and that's what you ended up getting as a resultant physical property models. So that's my understanding. I could be a little bit wrong, but might be mostly right.
Thank you. And my last question would be about chargeability. So you said that that's basically depends on the, what did you say? The porosity, yeah? So that means any porous rock would be seen equally well in the geophysical data. And if it's, I don't know, a large fault where you have more porosity because of the high deformation, that would also be possible to map it with the chargeability. And
that's kind of a bit of stretch, because what I mentioned was clays are chargeable. and the volcaniclastic and pyroclastic can include clays, right? So the first level is it chargeable? So the chargeable means can it build the charge? Can it actually store the energy and release it slowly? So that's the chargeability. And the clays are typical material that can be chargeable. So any materials including clay, it could be chargeable. That's fine. And the pore size or the surface area of the pore is really sensitive to the rate of decay. And that's what I meant, pore size. So if you have a greater pore size, it'll decay slowly. If you have a very small pore size, it'll decay fast. So that determines the sort of the characteristics of the decay, the chargeability decay.
But still, if you have a fault, and fault can be lined up by clay-rich rock because it experienced some hydrothermal alteration and produced clays, so that you can map a fault. Yeah.
I think so. If that clays are not consolidated, I guess, then I think it'll show up as a chargeability anomaly.
Okay, does anyone else have any more questions for Seogi?
I guess, can you give other examples of chargeable rocks, not just clays? That might be interesting for the audience.
Permafrost is actually chargeable, so it may not be a good example, but it actually makes it challenging because that Do27 was actually located at the permafrost area, so the background was actually chargeable, but that permafrost decays very, very quickly, so it didn't actually show up in our airborne data. So that's one example. But if you actually measure on the ground, you can actually clearly see strong negative transients. And the other example, so some other minerals like a fine grain, I'm not sure you guys are familiar with Mount Milligan. Mount Milligan, not McMilligan, Mount Milligan. So if the sulfides are fine grained, so it's a fine grained mineralization can also actually generate this strong chargeability effect. And what we are seeing is the very fast decaying, but sometimes actually, if you think about the porphyry, what's called induced polarization technique on the ground, that's the major tool used to find the porphyry deposit because these sulfides are very chargeable. But what we can pick it up with the airborne setup is very fine grained, like sort of the sulfide. Yeah, I'm not sure if there's any other typical example with chargeable. But those are sort of the major permafrost, clays, and the minerals, metallic minerals like sulfides.
Thanks.
Okay. Well, if no one else has anything else to add, I will stop the recording now and then we can just kind of chat a little bit more informally here.